And now we continue. So now we try to solve for alpha. So multiply them out. So we have p times 1 minus alpha is equal to 1 minus p and 1 plus alpha. And from here we have p minus alpha. P is equal to 1 minus p and plus 1 minus p alpha. Now remember, we are trying to solve for alpha, so we don't really need to multiply everything out. And then we move terms around. So we have p minus 1 minus p is equal to alpha p and plus 1 minus p alpha. So we have over here alpha is equal to 2p minus 1. And remember, this is our candidate. This is our candidate for maximum. Okay. Now, once we have this candidate, we need to test. So need to test. This is an important step. Need to test if alpha star is between 0 and 1. What it means is that, is it true that alpha star is less than 1 and alpha star is bigger than or equal to 0? Okay. Now, if we look at 2p minus 1, p, the maximum value is actually 1, less than 1. So 2p minus 1 is going to be less than or equal to 2 minus 1, which is 1. So this is true. So alpha star is less than 1. But how about alpha star bigger than or equal to 0? Is it true? Is it 2p minus 1 bigger than or equal to 0? And then we look at this one over here. That means 2p minus 1. And 2p must be bigger than or equal to 1. And that means p bigger than or equal to 1/2. But that's not true, because what it means if p is less than 1/2, alpha star is not valid. It's not a valid candidate, so we don't need it. Okay. So now what it means is that we have to solve this problem in two different cases. The first case is when p is bigger than or equal to 1/2. Here we have three candidates. We have three candidates. We always have the end points. That means we have 0 and alpha star and 1. But on the other hand, it's easy to check. It's easy to see. We can find f double derivative of alpha. We always do this. If you look back, if we do the double derivative, then this is what we have. We have negative p 1 plus alpha to the negative 2. And do the second derivative very carefully because of the chain rule. We will have negative 1 minus p. And again, we will have negative 1 minus alpha to the negative 2 and another negative 1. So we have negative p 1 plus alpha to the negative 2 and negative 1 minus p 1 minus alpha to the negative 2. Both terms are negative, so we have this one less than 0. So what it means is that alpha star is equal to 2p minus 1 must be the maximum. The reason is that we have a concave downward function. And that's the maximum value we have. So now let's try to find v1. So v1 of x is going to be, plug alpha star inside and look at the function we had before. So we have log x over here and plus p, and we have log 1 plus alpha, so 1 plus 2p minus 1, so this is 1, and plus 1 minus p, and log 1 minus alpha, 1 minus 2p, minus 1, but it's negative, so it becomes positive. Okay, so that's what we have. So let's simplify this one a little bit, and then we have log x plus p, and this is log 2p, and this one over here is 1 minus p, and this is log 2 minus 2p. Okay. Now, the constant over here depends only on p, no x inside. So this one is the constant. Depends only on p. And we're going to call this constant c over here. So what we have over here is that v1 of x is equal to log x plus some constant c, which is specified over here. We call this constant c. And this is another afterthought, because you will see to carry this big constant around in the computation is kind of difficult and messy. So we just look at this one over here, then it's clean. And remember, v naught of x is equal to log x. And somehow we probably don't see the pattern yet. And if you want to see the pattern, maybe you want to go forward just one more step. Well, we will see that very soon. So v2 of x, let's try one more time. And that's the maximum. And we have alpha less than equal to 1 and bigger than equal to 0. And then we have, again, p. We have v1 over here. Now, x plus y becomes x plus alpha x and plus 1 minus p, and v1 x minus alpha x. Okay. So from over here, now we need to use this v1 of x. So remember, v1 of x is log x plus c, right? And then we're going to plug it in over here and plug it in over here. So this is what we have. We have maximum alpha less than equal to 1, bigger than equal to 0. And we have p over here. Just do it very carefully. It's log. Now x becomes x plus alpha x plus c. Put a pair of parentheses over here. And then 1 minus p. And then here again, log. Now x becomes x minus alpha x and plus c, because we are using v1 now. So if you look at this expression, this is very similar to the previous one, but let's try to see what we have. We will have p log x plus p log 1 plus alpha and plus pc, and plus 1 minus p log x again plus 1 minus p and log 1 minus alpha and plus 1 minus pc. Now, that's really a long expression, but on the other hand, it's not too hard to see how to combine them, because you see over here, p log p, 1 minus p log x, p log x. This one, if you add them up, it's going to be simply log x. And this one over here, p times c and 1 minus p times c. If you add them up, it's just going to be c. So we end up with a very similar maximization problem. So we have log x plus c, and then plus maximum over here, alpha less than 1, bigger than 0, and we have p log 1 plus alpha, and plus 1 minus p, and log 1 minus alpha. Now, if you go back, if you look at the maximization problem over here, this is exactly the same as the one we had earlier over here, and the one that's underlined by green line over here, right? That's exactly the same. The only difference is now we have a c in the front. So now we know we don't need to solve this over again. We already know the maximum value is just c. So this one over here is log x plus c and plus c again, and which is log x plus 2c. Now let's list these first three values. v of 0 of x is log x, and v1 of x is log x plus c, and v2 of x is log x plus 2c. So we know what's going to be our proposal. So we actually see this is our inductive assumption. Obviously, we see that we guess v of n of x is going to be log x plus nc. And we can easily use induction to solve it because assume this, we already verified the first step. So assume v minus 1 of n of x is log x plus n minus 1c, right? And then we plug it into the general Bellman equation. This is the maximum alpha less than 1 bigger than or equal to 0, and p, we have vn minus 1 x plus alpha x and plus 1 minus p, and vn minus 1 x minus alpha x. So if we use the same algebra, we will see this is going to be the maximum alpha less than 1 and bigger than or equal to 0. Let's just put it inside one more time. So p over here becomes log x plus alpha x plus n minus 1c, right? And then plus 1 minus p and log x minus alpha x plus n minus 1c. Okay. Using the same thing, let me skip over here just one step. So this, we will have log x plus n minus 1c and plus the same maximization problem. Alpha between 0 and 1, and we have p log 1 plus alpha and plus 1 minus p log 1 minus alpha. And again, this last part over here, this part over here is equal to the same c, which is, if we remember, it's going to be p log 2p and plus 1 minus p log 2 minus 2p, because we have exactly the same alpha star, which is 2p minus 1. Okay, and plug it in, that's what we have. The same c, so this is going to be log x plus n minus 1c plus c, and then it's log x equal to plus nc. So this is correct. So by induction, we know that's what we have. So by induction, we have proven that Vn of x is log x plus nc. Now the case when p is less than 1/2 is easier. So we will not do that anymore. And let's just write down the result we're going to have. When p is less than 1/2, this optimization problem, this one over here, p log 1 plus alpha plus 1 minus p, 1 minus log 1 minus alpha. This maximum value is obtained when alpha is equal to 0. Okay. The reason is you can actually see in this case, if we call this function still f of alpha, f of 0 is going to be just 0. But f of 1 is negative infinity. And that's why f of 0 equal to 0 is the maximum. And because this value maximum is 0, so we will see that v1 of x is equal to v0 of x is going to be equal to log x. There's no change. And later on, by induction, we show that v1 of x is also equal to log x. And the meaning is very clear, because When alpha equal to 0, when p is less than 1/2, that means it's not likely to win. The optimum policy, alpha star, is equal to 0. So the initial value, the initial amount, x is the same, remains the same. Remain the same for all n periods. So eventually we still get x, and the utility is just log x.